To meet these demands, the modern engineering paradigm has shifted definitively toward a multi-barrier approach. This architecture does not rely on a single breakthrough unit process. Rather, it strategically couples physical separation, chemical destruction, and biological assimilation. In this episode, we dissect the core unit processes defining modern advanced treatment: ozone oxidation, advanced oxidation processes, or AOPs, granular activated carbon, biological activated carbon, and targeted PFAS control. We will explore their operating principles, kinetic constraints, design trade-offs, and common failure modes, so you can evaluate how these technologies apply to your specific water matrix. The conceptual cornerstone of modern water treatment is the multi-barrier framework. When raw water sources are impacted by industrial discharges, agricultural runoff, and climate-driven hydrological shifts, relying on redundancy across multiple physical and chemical mechanisms is essential. According to United States Environmental Protection Agency technology frameworks, no single unit process can reliably remove the entire spectrum of inorganic, organic, and biological contaminants found in contemporary watersheds. The multi-barrier train operates on a principle of sequential vulnerability targeting. Pre-treatment and conventional clarification remove suspended solids and bulk natural organic matter. However, dissolved micropollutants, including per- and polyfluoroalkyl substances, or PFAS, taste and odor compounds like geosmin and 2-methyl-isoborneol, and pharmaceutical residues slip past conventional barriers. Advanced unit processes are therefore positioned downstream to tackle these persistent compounds. Crucially, integrating these processes requires careful hydraulic and chemical coordination. For instance, introducing an oxidant too early can alter natural organic matter fractions, whereas placing adsorption media downstream of inadequate suspended solids removal leads directly to premature pore clogging. Engineers must evaluate how each barrier interacts with upstream water quality parameters, particularly specific ultraviolet absorbance, or SUVA, and dissolved organic carbon profiles. Our first advanced unit process is ozone oxidation and its integration into advanced oxidation processes, or AOPs. Ozone, O3, is a powerful oxidant generated on-site by passing oxygen or dried air through a high-voltage electrical discharge field. When injected into the water stream, molecular ozone reacts via two distinct pathways: direct, selective oxidation by molecular ozone itself, and indirect oxidation driven by the formation of non-selective hydroxyl radicals when ozone decomposes in water. The fundamental mechanism of an advanced oxidation process, or AOP, is the rapid generation of hydroxyl radicals, which possess an oxidation potential of 2.8 volts, significantly higher than molecular ozone or chlorine. These radicals non-selectively attack and cleave refractory carbon-hydrogen and carbon-carbon bonds. However, designers must exercise caution. AOPs and ozonation do not mineralize all target compounds completely. They can transform parent molecules into intermediate oxidation byproducts. Furthermore, in bromide-containing waters, ozonation inevitably oxidizes bromide ions into bromate, a regulated carcinogen, requiring strict dose control, pH depression, or ammonia addition to suppress bromate formation. Moving downstream, granular activated carbon, or GAC, remains a foundational technology for the sequestration of synthetic organic chemicals, most notably per- and polyfluoroalkyl substances, or PFAS. GAC is manufactured from carbonaceous source materials such as coal, coconut shell, or wood, activated under high temperatures to create an extensive internal network of macropores, mesopores, and micropores, yielding a massive specific surface area per unit mass. The removal mechanism in GAC contactors is physical adsorption. Contaminants migrate through the boundary layer surrounding the carbon granule, diffuse into the pore network, and attach to internal surface sites via van der Waals forces. Full-scale liquid treatment for PFAS relies heavily on sequestration technologies like GAC and ion exchange, as complete chemical destruction remains largely impractical at municipal flow scales.
However, engineers must understand the critical limitations governing carbon adsorption, particularly regarding PFAS chain length. GAC exhibits high adsorption capacity and favorable partition coefficients for long-chain perfluorinated compounds, such as perfluorooctane sulfonate, or PFAS, and perfluorooctanoic acid, or PFOA. Conversely, short-chain PFAS, such as perfluorobutanoic acid, or PFABA, and perfluorobutane sulfonate, or PFAS-BS, possess higher aqueous solubility, lower hydrophobicity, and much weaker affinity for carbon-active sites. Consequently, short-chain compounds experience rapid mass transfer zone migration and premature breakthrough, often exhausting beds long before long-chain capacity is reached. To extend media life and optimize operational economics, modern treatment facilities frequently transition traditional GAC contactors into biological activated carbon, or BAC, systems. When upstream ozonation breaks down complex refractory natural organic matter into smaller, highly biodegradable fragments, the resulting ozonated water is fed directly onto GAC beds without intermediate disinfection.
From a process design perspective, biological activated carbon operation requires careful control of dissolved oxygen concentrations, backwash frequencies, and nutrient balances. Excessive shear forces during backwashing can strip the active biofilm, while insufficient oxygen limits aerobic biological degradation. Operating engineers must continuously monitor effluent biological stability to prevent microbial breakthrough into the downstream distribution network. Successful implementation of advanced treatment trains depends on rigorous adherence to key design and operating parameters. Among these, empty bed contact time, commonly designated as EBCT, is the primary volumetric design criterion for GAC and BAC contactors. EBCT is defined as the empty volume of the carbon bed divided by the volumetric influent flow rate. For effective PFAS sequestration and micropollutant control, standard engineering designs typically specify EBCT values ranging from 10 to 20 minutes, depending on empty bed hydraulic loading rates and target compound treatability. Equally critical is the characterization of influent organic carbon using specific ultraviolet absorbance, or SUVA, calculated by dividing the ultraviolet absorbance at 254 nanometers by the dissolved organic carbon concentration. A high SUVA value indicates hydrophobic, high molecular weight organic matter that is readily removable via coagulation and absorption, whereas low SUVA values signify hydrophilic, low molecular weight compounds that challenge conventional carbon removal. Hydraulic loading rates typically range between 5 and 10 gallons per minute per square foot, ensuring adequate residence time within the mass transfer zone, or MTZ, where adsorption kinetics occur. Engineers must model the migration of the absorption wavefront through the column, scheduling lead-lag contactor configurations to ensure that the primary bed can be taken offline for media exchange before effluent concentrations exceed regulatory thresholds. Despite careful design, advanced treatment systems are susceptible to specific operational failure modes that every plant engineer must anticipate and mitigate. The most prevalent failure mode in carbon-based systems is competitive absorption interference caused by natural organic matter, or NOM. Bulk NOM molecules occupy high-energy absorption sites, drastically reducing the effective capacity available for target micropollutants. In ozonation and advanced oxidation process systems, failure modes include inadequate radical scavenging control, where high alkalinity or carbonate concentrations consume hydroxyl radicals before they can oxidize target pollutants. Furthermore, mechanical or electrical failures in ozone generators lead instantly to primary disinfection and oxidation failure, requiring automated fail-safe diversions to protect public health. Given the capital-intensive nature of advanced treatment infrastructure, how should engineering consultants and utility managers approach technology selection? We apply a structured, site-specific decision framework comprising 4 sequential phases. First, comprehensive raw water characterization. Utilities must perform seasonal water quality profiling, quantifying natural organic matter fractions, SUVA, bromide levels, and specific targeted micropollutants across hydrological cycles.
Second, regulatory compliance mapping. Engineers must align treatment objectives not only with current federal primary drinking water standards, but also with projected future statutory thresholds. Third, mandatory pilot scale and bench scale testing. Because water matrices vary significantly between surface water reservoirs and deep alluvial aquifers, column studies and rapid small-scale column tests, or RSSCT, are indispensable for determining site-specific GAC usage rates and empty bed contact times. Fourth, life cycle cost-benefit analysis. Designers must weigh capital expenditures against operational expenditures, factoring in media reactivation frequency, energy consumption for ozone generation and ultraviolet lamps, and residuals management. Advanced drinking water treatment in 2026 is no longer a futuristic luxury. It is an engineering necessity. By mastering the synergy of ozone oxidation, advanced oxidation processes, granular activated carbon, and biological filtration, water professionals can construct robust multi-barrier defenses that safeguard public health against emerging chemical threats. However, as we remove contaminants from our drinking water sources and concentrate them via advanced separation technologies, a critical engineering question remains. What happens to the concentrated residuals, brine streams, and waste streams generated by high recovery systems? In our next episode, we cross over to desalination engineering, examining high recovery seawater reverse osmosis, isobaric energy recovery devices, and advanced zero liquid discharge, or ZLD, brine management. Thank you for watching Water Atlas. Subscribe for rigorous engineering-grade insights into the infrastructure shaping our water future.